What if the best way to prevent your complex systems from failing spectacularly was to break them on purpose? This sounds counterintuitive, but it's the core idea behind chaos engineering. It's not about causing chaos. It's about revealing the chaos that already exists in your systems. Think of it like a vaccine. By injecting a small, controlled failure into a system, you force it to build immunity, making it stronger and more resilient for when a real disaster strikes. Why is this necessary? Because modern applications are unbelievably complex. We've moved from simple, single structures to vast, interconnected ecosystems of microservices. In this complexity, you have unknown unknowns, weaknesses and dependencies you can't possibly predict with traditional testing methods. When one of these hidden faults triggers a real outage, the result is downtime. That means frozen checkout pages, failed logins, and frustrated users. Chaos engineering provides a way to find these weak points proactively in a controlled environment before your customers do. The process starts with a hypothesis. You ask a what-if question, like, what if our primary database becomes unavailable for 30 seconds? Next, you design and run an experiment to simulate that failure. This is called fault injection. It could be increasing CPU usage, introducing network latency, or taking down a server. While the experiment runs, you observe everything. This is where observability is key. You monitor metrics, logs, and traces to see exactly how the system behaves under stress. A crucial part of this is measuring the blast radius. Did the failure stay contained as you expected, or did it cascade and cause unexpected problems in other services? If you find a weakness, say your system didn't fail over to the backup database correctly, you've discovered a valuable lesson. Now you halt the experiment, fix the issue, and strengthen the system. The goal is to make the system automatically withstand that failure in the future. Over time, these experiments can be automated, creating a system that is constantly being tested and hardened against failure all on its own. Teams often start with GameDays, which are planned, manually run chaos experiments where everyone gathers to observe the impact and practice their incident response. For safety, you always start small. Your first experiments should be in a testing or staging environment, never in production. The goal is to learn, not to cause an actual outage. As you build confidence, you can gradually increase the scope, moving from staging to a tiny fraction of your live production traffic. Critical safety mechanisms are built in. Every chaos experiment must have a big red button, an immediate and easy way to stop the test if it has an unexpected impact. So what are the real-world benefits? First and foremost, you build truly resilient systems that can gracefully handle turbulent conditions. You dramatically reduce the frequency and duration of costly outages, leading to higher availability and happier customers. Your teams also get better at responding to incidents. Mean time to recovery, or MTTR, improves because they've practiced responding to failures in a safe environment. One of the biggest advantages is uncovering hidden dependencies. You'll find connections between services you never knew existed until you see how they fail together. Ultimately, this builds confidence. Not hope, not assumptions, but real evidence-based confidence in your system's ability to withstand failure. And it fosters a powerful cultural shift. It moves teams away from a fear of failure and towards a culture that treats failures as invaluable learning opportunities. You move from asking, will our system fail, to how will our system behave when a specific component fails? It's a subtle but profound change in perspective. Companies that embrace chaos engineering find they can innovate faster because they're not afraid that new features will break the entire system. So, chaos engineering isn't about recklessly breaking things. It's the disciplined, scientific practice of finding weakness before it finds you. By embracing and learning from controlled failure, you build systems that are robust, dependable, and truly unbreakable when it matters most. What's the biggest what-if failure scenario in your work? Share it in the comments below, and subscribe for more insights into building better software.